Hi everyone. In this example, we're going to use momentum conservation to solve a two-dimensional collision problem. So here's the problem. Mo, who has a mass of 80 kilograms, and Joe, who has a mass of 50 kilograms, collide while ice skating. Just before the collision, Mo is skating directly south with a speed of 10 meters per second. Just after the collision, Mo and Joe are moving together, they're holding on to each other, and they're traveling with a speed of 6 meters per second at an angle of 60 degrees south of east, and that's just after the collision. Our task is to find Joe's velocity, that's a vector, just before the collision. In solving this problem, I'll use a coordinate system in which x is the easterly direction and y is to the north. Also, I've made an initial guess as to Joe's rough initial direction. Obviously, Joe's got to have some eastward velocity component because Mo and Joe together have an eastward velocity component, and Mo had no initial eastward velocity component. So whatever eastward velocity component is carried in the system had to come from Joe. But whether Joe has a northward or a southward velocity component, without actually calculating the problem, can be hard to tell. So it doesn't matter that we don't exactly know this direction. We will solve for Joe's north or southward velocity component and east or westward velocity component, and the signs will indicate which of those directions are appropriate. And we'll see how that comes out. Okay, so let's solve the problem. First, we note that we have a collision. Now, when we see collision, we should immediately be thinking of the role of momentum. And that leads us to the impulse momentum theorem, which says that the change in momentum of a system is equal to the impulse delivered to that system. Now, impulse itself is a product of force and time interval. Now, if the time interval that we're considering is very small, the product of time interval and the average external force will be small. And so if this time interval is small enough, the external impulse will be negligible. And then if that's negligible, the change in momentum of the system will be approximately zero. Now in our particular problem, which is happening on ice, this average external force exerted by the ice on the skaters, that's going to be small, and so that actually gives us latitude to have a longer delta t and still have a small or negligible external impulse. But it's worth pointing out that even if we had a high friction situation, if this collision were happening on concrete instead of ice, if we took a small enough time interval, then even with a substantial external friction force, we could still have a very small or negligible impulse. Also note that since impulse is a vector, we could apply the impulse approximation component by component if necessary. So, returning to the problem at hand, we apply the impulse approximation, so the change in momentum of our system for this small time interval will be zero, which means the initial momentum of the system and the final momentum of the system will be equal. Let's apply this in our x and y directions. So the system's initial x-component momentum must be equal to the system's final x-component momentum. Now the initial x-component momentum can have contributions from Joe and Mo, while the final system x-component momentum, we've got Joe and Mo moving together, so I'll write it like this. Note, however, that Mo has only a velocity component in the y direction, negative y direction actually, so Mo has no initial x-component of momentum. Meanwhile, Joe's initial x-component of momentum will be the product of Joe's 50 kilogram mass and his initial x-component of velocity. Similarly, the final x-component of the momentum of Mo and Joe together will be their combined 130 kilogram mass multiplied by the x-component of their final velocity, which would be 6 meters per second cosine of 60 degrees. Solving for the x-component of Joe's initial velocity, we get 7.80 meters per second. Before moving on, let's do a little reality check. This came out positive. The positive x directions are easterly direction, and we do indeed expect that Joe had an initial x component of the velocity that was in the easterly direction. So let's move on to the y direction. In the y direction, we'll have Joe's initial y component of momentum. That'll be 50 kilograms times v sub iy for Joe. Now it may be in the positive y direction or the negative y direction. We don't know. So this v sub iy will carry that directional information, as we'll see shortly. For Mo, we have Mo's momentum will be the product of Mo's mass of 80 kilograms and Mo's y component velocity, which would be 10 meters per second in the negative y direction, so we'll have to include the minus sign for that. And then finally, after the collision, the y component of the final momentum will be Mo and Joe's combined mass of 130 kilograms multiplied by the y component of their final velocity, which will be 6 meters per second times a sine of 60 degrees, and with a minus sign included to indicate the negative y direction. Solving for the y component of Joe's initial velocity, we get 2.49 meters per second. Finally, we can express Joe's initial velocity in terms of the unit vectors I and j, or in terms of the magnitude and a direction. This magnitude is found in the usual way by taking the square roots of the sums of the squares of the components. This directional information, we just use the arctangent of opposite over adjacent. And finally, this north of east designation indicates that this direction here of Joe's initial velocity, if you start from east, you go 17.7 degrees north from east, or north of east. All right, that's it. Thanks for watching.